Welcome to Calculus 1. So this video is just going to be a short introduction of the kinds of problems we're really using calculus to solve. They say calculus is the study of change. And that is in fact what we're doing. What we're really interested in are problems that came first out of physics, which is Newton and Leibniz were trying to solve questions about bodies' motion, velocity, acceleration, force, that sort of thing. But the bigger picture is when you look at those kinds of problems, you're looking at something which has a function, for example, a velocity function, force function, and that function is changing in time. So you might want to find out what's going on at a specific instant in time, but the function is changing in time. So you have to figure out what that means, especially when it's something like velocity, which is originally, let me talk about the velocity problem, for example. So the velocity problem, what is velocity, right? Velocity is going to be sort of how fast you're going, right? So it's the change in position over the change in time. So this is an average, really. So if we call position x, and we're just going in one dimension, nothing hard here, just straight line, back, forth. So change in position, let's say your position at time 2 minus the position at time 1, divided by the change in time. So time 2 minus time 1. And what you'll see a lot in calculus is that we write this with a delta, delta being the change. So the change, this literally change in position over change in time. The delta meaning x2 minus x1. So we'll see that notation a lot, right? If you think about this though, this is an average, okay? If I'm talking about, say I'm driving from Detroit to Ann Arbor, and say it's 40 miles, it takes me 40 minutes, so I know I went 60 miles an hour. But that's the average over the whole time. It's not telling me what's happening at every instant. And as you know, either you're stuck in traffic or you're trying to make it up. So you're not going 60 miles an hour straight from your beginning point to your end point. Your velocity is changing. So like when you're trying to make it up and you get caught on the radar and the cop says, ma'am, you're going 90 miles an hour. Right? How does he know you're going 90 miles an hour at that instant? You can say, well, I know it's just going to take me 40 minutes to take this trip, so obviously I'm going 60 miles an hour, officer. That's not going to fly, and you know it. Why? Because he's not looking at your time from Detroit to Ann Arbor, the whole thing. He's looking at a very small amount of time, which is that little amount of time that he caught you on the radar. Now, the radar gun also knows your velocity because it's taking the change in your position over the change in time that's measured by the radar gun, right? So this delta t for the cop is a very, very small amount of time. It's not zero. It's not instantaneous, right? You can't get that measurement, and it doesn't make sense if I put 0 here, because that would mean I'm dividing by 0. Like, I can't divide by 0, right? So this is really an average velocity. And the question is, if I truly want to make sense of velocity, though, as a function, if I wanted to write my velocity, let's call it v, as a function of time on my trip, and this just gives me some mathematical quantity, right, some mathematical expression, then I can put in, say, what's my time at 2, or 2 minutes, or 6 minutes, and that's going to give me a number, but it's going to give me an instantaneous velocity, the number at that time, right? So that's what we're after. But that doesn't make sense exactly with this, because what I want to say is that that instantaneous velocity is what happens when I take this delta t, this change in time, and I take it to 0. Okay? And we have to mathematically make sense out of that. The only reason it works is because if I take this close to 0, this guy is also going to get close to 0, right? Because my position is changing with respect to time. So rather than, I have 0 over 0, so what that means is I'm looking at something that doesn't mean anything, okay? This is where calculus comes in, because it allows us to give a meaning to that. And we give a meaning to it by using the derivative. So we'll be talking about that pretty soon, but this is the idea, and really it's the process of taking a limit, okay? We're taking this delta t smaller and smaller and smaller. It may never be equal to 0, but it's very, very close to 0. It's infinitesimally close to 0. So that's really what we're looking at. That's the velocity problem. You can also think of this same thing in a more geometric context. And it's in fact the same problem, but from a geometric perspective, we call this the tangent problem. So it's just, some people like to think of things physically. Some people find it easier to think of things in a geometric sense. So whichever way you want to think about it. The tangent problem is something like this. I've got some known function f, right? And what I want to do is find the equation of the tangent line. Okay, so what is the tangent line? It's a line that touches the function at just one point, and that's it. So if you remember, like for a circle, the tangent line is like this, right? If I'm going through in 2 points, that gives me a chord. But the tangent line only touches it at one point. I'm going to get rid of that. It doesn't even look like a circle. All right, so that's what we're doing here. But again, in order for something, I'm going to call this point A. In order to find the equation of the line, so I know a point on the line because this point is a point on the curve. So I know what the coordinates of that point are. But in order to find the equation of the line, I need a point and a slope. The problem is I only know one point on this line. I don't know what any other points are. So how am I going to find the slope? So this is another way in which calculus will help us. We'll see how this works, but again, it's a limiting process, and it looks mathematically the same as the distance problem, because look what happens. Forget this one for a moment. I'm going to take another one, call this B, and I'm going to draw a different line. Okay? So this is the tangent line. And what do I call this other one that goes through 2 points? I call it a secant line. And for this secant line, I can easily find the slope. Right? Let's get rid of this for a second. I'll write it over here just really quickly. So this is going to be the slope, right? Is the change in y over the change in x. It's rise over run. So in this case, this is f of b. And this is f of a over b minus a. So I know the slope of the secant line. Okay? Now, what calculus is going to do, very similar to what we were saying about the delta t, the difference in time going down, we're going to take this point B, I'm going to move it closer. And I'll give you a nice visual later on when we're really talking about this so you can see how this works in real time. And you can imagine as you move this point closer, that line is going to move closer and closer and closer and closer to that tangent line. So if we can make sense mathematically out of taking this and taking b minus a to 0 and have it make sense, which doesn't always work, but in many cases it does. So if we can make sense of that, then we can define this tangent line. And sometimes, as I said, it doesn't work. Sometimes we can't do it, in which case we can't find a tangent line. So these things don't always work. Okay, that's another important thing. So those are primarily the two problems that we're going to be looking at through the majority of Calc 1. And those are problems talking about the derivative. So this difference quotient here, this becomes the derivative. There's one problem that we'll talk about at the very end a little bit. That's called the area problem. Okay? The area problem is also something we solve with calculus. The area problem comes from just thinking about, let's say, how would we find the area of some object like that? Well, it's not easy, right? So you could find, you know how to find the area of a square. Okay, we know a circle is pi r squared. We're doing area today, right? If I have something that is sort of weirdly shaped but is still a polygon, since I know how to find the area of a triangle, I can break this up into whatever, some kind of triangles. I can find the area of all those triangles, so I can find the area of this kind of shape. But when it's curved sides, and it's curved sides that aren't like that. So if I like added a circle here and I knew it was a circle, I could find the area of that. But if it's something bizarre like this, even if I know what these points are, it's not easy to figure out what it is. So this problem is remarkably, it's very different than your tangent and velocity problems. Those are related. But it turns out that you can use sort of this idea of changing something and making it very, very, very small in order to do this problem. Okay? Which we will see it's going to be at the very end. But I'll give you just a really quick overview of this. I'm going to draw it a little bit easier to see. I'm just going to draw something like this so that we only have to think about one curved piece rather than curved pieces on all the different sides. So just like we can think about that secant line and different pieces getting closer and closer to something getting smaller and smaller, we're going to do something similar here, only we're going to be looking for the area. So if I want to make an approximation for the area here, what I could do is I could just break up this thing into some pieces, right? Okay, that doesn't help me very much yet because I can't find the area of any of these individual pieces because it's got that curved line. I don't know what to do with the curved line. But I'm just going to approximate it. I'm going to make it a rectangle. So it's not an exact answer, right? I'm going to make it a rectangle from the right endpoint. Doesn't matter. Right, so I'm just going to make these straight lines over. And now this, because I know what this function is, I can figure out each of these points. So I can figure out the area there, my shaded area, which I know it looks really crappy on this board, so I apologize, but you know. So I can figure that out. Again, it's not good, right? I've got this overshoot here, I've got this undershoot here. It gives me an approximation, but it's not a good approximation. The thing about calculus is we said, okay, we're going to now make something infinitesimally small. We can make it very, very small. So if we make this, if we take more rectangles, right, we're going to get a better approximation. And you know what? I'm not going to try and draw it because you won't be able to see it. But there is a video or two that will be linked where they do this nicely. You can see they do it with a computer. It's very pretty. But the idea is that we're just going to take this and we're going to make smaller and smaller rectangles. And as we have smaller and smaller rectangles, you get less overshoot and undershoot. And you can get to the actual area under that curve. So those are the three big problems we'll be talking about this semester.